If you were to drain the oceans, the seafloor appears to be a barren expanse of rock and mud, but these dark ridges and pitch-black plains serve as a continuous, physical ledger of Earth's biological and chemical history. Every day, billions of microscopic organisms living near the sunlit surface die. Their microscopic shells, made primarily of calcium carbonate, continuously sink towards the bottom in a process known as the planktonic rain. This map shows the distribution of sediments across the Pacific Ocean floor, revealing a stark geographical anomaly. The elevated mid-ocean ridges are coated in white, calcium-rich oozes, while the deeper adjacent basins are covered in a deep red clay. This distribution presents a paradox. The surface waters globally are teeming with life, producing a uniform planktonic rain, yet the deepest parts of the ocean floor contain zero trace of calcium carbonate remains. The composition of the ocean floor is dictated by a stripped filter. It is defined not by the biological matter that falls into it from the surface, but by the specific materials that chemically survive the miles-long journey to the bottom. The mechanism enforcing this filter is the carbonate compensation depth, or CCD. The CCD is an invisible, horizontal geochemical boundary in the water column that actively dissolves bone and shell. Typically hovering around 4,500 meters below the surface, this depth acts as a strict cutoff line. Above it, biological remains are preserved. Below it, they are systematically erased. This boundary determines exactly what survives to become geology. By tracking its movement over millions of years, we can measure the chemical state of the ancient atmosphere and the temperature of the oceans long before the first human records. Looking at this 2D cross-section of a standard ocean basin, we track how different sediments settle from the shallow continental shelf down to the abyssal plain. The first primary input comes from the land. Terragenous sediments, eroded rocks, volcanic ash, and dust drift over the open ocean, settling slowly to form deep-sea red clay. The second input is biogenous sediment, calcareous oozes formed by the planktonic rain. Originating from the sunlit photic zone, these shells fall much faster and in significantly higher volumes than the terrestrial dust. The sediment type that ultimately defines the seafloor follows a simple mathematical rule. Whichever material accumulates faster buries the other, dominating the sedimentary record. In shallower waters, the math is one-sided. The sheer volume of calcareous oozes quickly overwhelms and buries the slow-accumulating red clay. If accumulation relied purely on the speed and volume of falling debris, the entire ocean floor would be blanketed in white biogenous ooze. The existence of red clay at the bottom indicates a chemical intervention deeper in the water column that reverses the math. This dual-axis graph tracks the descent of a single calcium carbonate shell. As depth increases, we track temperature on the first x-axis and pressure on the second. Carbonate solubility follows a counterintuitive chemistry. It dissolves easier in extreme cold and under extreme pressure. Descending into the high-pressure depths, the water holds drastically higher concentrations of dissolved carbon dioxide. This excess carbon dioxide reacts directly with water molecules to form carbonic acid, turning the deep ocean into a corrosive environment for solid calcium carbonate. On its way down, the shell crosses a critical threshold known as the lysocline. This is the specific depth where the water becomes acidic enough that the dissolution of carbonate transitions from minimal to aggressively accelerating. Below the lysocline, survival is a matter of architecture. Thinner-walled planktonic shells dissolve rapidly, while thicker-walled benthic forms manage to resist the corrosion slightly longer. Further down, the surviving fragments hit the ultimate boundary, the carbonate compensation depth. The CCD represents a precise mathematical equilibrium. It is the exact depth where the rate of falling calcium carbonate is entirely canceled out by acidic dissolution in the deep water. Breaching the CCD threshold is structurally fatal. Every particle of calcium carbonate is stripped away by the acid, leaving zero trace of the biological rain. Only materials immune to this acid chemistry successfully accumulate below this line. This leaves siliceous oozes, made of glass-like silica, and fine iron-rich terrestrial dust. Red clay covers over a third of the global seafloor. It dominates the abyssal plains not because it is abundant, but simply because it is the only solid material durable enough to survive the ocean's corrosive depths. The CCD is not a static, flat plane that uniformly wraps around the globe. This comparison illustrates how the depth of the CCD actively fluctuates. On the left is a standard Pacific basin, and on the right is the equatorial Pacific. Here, cold, nutrient-loaded water upwells from the deep, driving massive biological productivity at the surface. This creates a concentrated calcareous rain. The volume of sinking shells arrives faster than the deep-water carbonic acid can dissolve them. Because the acid is overwhelmed, the local carbonate compensation depth is physically pushed down, settling 500 to 800 meters deeper. To physically retrieve this historical record, geologists rely on deep-sea drilling programs. Vessels like the Glomar Challenger utilize massive midship drilling derricks to extract cores directly from the abyss. Marine stratigraphy relies on these vertical sediment cores. By pulling a cross-section of the seafloor up to the surface, scientists obtain a physical timeline that reveals how an ocean basin evolved and how the global climate fluctuated over millions of years. This core profile from a mid-ocean ridge displays 3 layers: calcareous ooze, red clay, and solid carbonate rock at the bottom. The surface ooze is 2 to 5 million years old, and the underlying red clay is 5 to 23 million years old. This presents a physical contradiction. This core was extracted from a depth well below the current CCD. How did intact, 5-million-year-old carbonate ooze manage to accumulate on top of deep-water red clay in an actively corrosive environment? New seafloor at mid-ocean ridges sits above the CCD, allowing solid carbonate to form. Over 23 million years, this crust moves away, cools, and sinks below the CCD. Here, falling carbonate dissolves, so only red clay accumulates on the older rock. 5 million years ago, glacial intervals dropped atmospheric carbon dioxide levels, making the ocean less acidic and pushing the CCD boundary deeper. As the CCD fell below this specific seafloor section, the water became non-corrosive, allowing calcareous ooze to survive and blanket the red clay. By decoding these alternating layers of mud and clay, scientists possess a precise paleothermometer and CO2 gauge for Earth's ancient atmosphere. The distribution of these marine deposits forms an ongoing physical ledger of the global carbon cycle. Every layer of sediment documents the transfer of carbon from the atmosphere into the abyss, preserved across the span of geological time.